Hello? Oh, good morning. We're all waking up. I'm waking up. You're waking up. The microphone is waking up. Thank you so much for joining us for this excellent set of talks that we're about to see early in the day. Our first presenter is Arpit Gupta. He's a recent Princeton PhD grad. He's joining Columbia as a postdoc for this next year before starting on the faculty at UC Santa Barbara. He is recruiting students for next fall, so send your brightest students to work with him. Tell them that they want to work with junior faculty. Junior faculty are great. And tell him about the awesome research that you're about to learn about called Sonata.
All right. Thanks, Justine, for the introduction. So today I'll be presenting Sonata, a query-driven streaming network telemetry system that is both flexible and scalable. So the onus of making the network is on network operators. However, in recent years, with the proliferation of internet-connected devices and applications, the complexity of network management has increased significantly. To keep the networks running, network operators have to handle various events such as outages, congestion, and cyber attacks. And to handle all these events, the first thing they need to do is to detect these events, right? That is the need to perform network monitoring. Now, to understand the requirements of a network monitoring system, let's consider a simple example. Here we have an attacker which sends spoofed DNS request messages to open resolvers, and the response to these requests get reflected to the victims. And as the number of responses increase, the victims get overwhelmed. Now, if I'm a network operator and if I want to figure out if hosts in my network are a victim of this attack or not, I would like to find out if there are hosts that receive DNS responses from many distinct sources, right? And notice in this task, the network operator is trying to extract and aggregate metric from a subset of the traffic. And there are so many ways in which we can define what subset of traffic it is interested in and what kind of metric it wants to extract. So while designing network monitoring systems, it is very important that we make sure that they are as flexible as possible. So now that we have established that network monitoring systems need to be flexible, we need to understand that the amount of storage and compute resources available for these network monitoring systems is limited. And this creates a gap between desired flexibility and scalability. So in today's talk, I will present you a system, Sonata, that tries to bridge this gap. More concretely, I'll be talking about the abstractions that make it possible for network operators to express wide range of network monitoring tasks, and the algorithms that make the best use of limited storage and compute resources. And of course, the system that glues the high-level abstraction with the low-level algorithms. So as you can imagine, building a network monitoring system which is both flexible and scalable is going to be a very challenging task. The first challenge that we need to think about is what is the abstraction that we should expose to these programmers so that they can express wide range of queries for wide range of network monitoring tasks. And once we have provided this abstraction, we need to figure out how are we going to scale the queries for these network monitoring tasks. Let's first talk about the programming abstraction. Here, a packet in a network carries a lot of information in its packet's header as well as the payload fields. But with recent developments in the programmable switches, a packet also carries a lot of meta information, which captures the state of the network. For example, a packet carries information about what was the queue size that it observed, or what were the hops it traversed in the network. So unlike many existing network monitoring systems that operate at much coarser level of granularity, Sonata operates at packet level of granularity. And it lets network operators operate or use or treat packet fields as tuples. And it also lets them express their monitoring tasks as data flow queries. Let me try to unpack this with an example here. Let's revisit the example that we were talking about earlier. Here, the network operator is trying to identify if the DNS response messages from unique DNS servers to a single host exceed a threshold, right? Let's try to see how network operator can express a query using data flow operators. So it is interested in finding victim IP addresses, and it will be operating over a stream of packet tuples. The first thing it will do is that it will apply a filter operation so that we are only operating or looking at the stream of DNS responses. Then, because it is interested in finding the responses from unique DNS servers, So it will try to apply a map operator so that we have this pairs of destination IP and source IP. Then it will apply a distinct operator so that we have unique pairs of destination IP and source IP. And once we have that, it can replace the source IP with 1 and just apply a reduce operator so that now it has count of unique source IPs for each destination IP. And finally, once we have that number, we can just compare it to the threshold to figure out which are the IP addresses victim of this attack. So this is just one simple example where we can express this high-level network monitoring task using data flow queries, standard data flow operators which are familiar to the network operators. And we observed that this was very helpful because we were able to express a wide range of network monitoring tasks in fewer than 20 lines of code. So now that we have allowed network operators to operate at all packet fields and all packets in the network, we have set ourselves against a very steep scalability challenge. So we have to figure out how we're going to execute multiple queries for high volume traffic in real time, right? So now we have to figure out how we're going to scale the query execution both as the number of queries and as well as the volume of traffic increases. To address this challenge, the first question that we need to address is what is the target that we are going to use for compiling or executing these queries? So in the past, all the network monitoring systems that offer this level of flexibility, they use CPU for query execution. And CPUs are awesome because you can extract or parse headers as well as payload fields. You can apply any action you want, and the stateful memory that is available for these stateful operators is of the order of gigabits. The problem is that they process packets at order of microseconds, which is much slower. Now, one can argue that you can use state-of-art scalable stream processor to horizontally scale the computation, but the challenge is that the problem that they cannot process packets at line rate still holds true. And if we want to use them, we still need to capture packets from the data plane and then send to CPU for further processing. An alternate solution is that we can use programmable switches. Though these programmable switches can process packets at the line rate, but they offer limited flexibility. There's a limit on how many or how deep they can go and what type of packet fields they can extract. The kind of operations they can perform on the packet are also limited. The state that is also available is of the order of megabits. Please excuse me, I'll drink some water. All right. I was not able to speak, sorry. So as I was saying that in contrast, we can use programmable switches because they can process packets at line rate. However, they offer limited flexibility because there is a limit on how deep you can go and you can what kind of packet fields you can extract. And also the operators or operations that they support is also limited. Plus the amount of stateful memory that is available is also very limited. So rather than focusing on choosing just one type of device for executing query, we started exploring, can we use both switches and CPU for query execution, right? And before I talk about how we can use these programmable switches for query execution, let me give you a brief overview of packet processing model for PISA targets. So devices that are based on PISA, which is a protocol-independent switch architecture, they have a programmable parser. So this programmable parser can extract user-defined packet formats and store the parse value in a fixed-length packet header vector. And a switch will have a pipeline with multiple stages. Each stage will have multiple reconfigurable match action tables composed of these TCAMs, ALUs, and SRAM. And a pipeline will have multiple such stages. At the end of the pipeline, we will have a deparser that will serialize this packet header vector back into a packet, right? So given this background of like how packet processing is done in these programmable switches, let me try to make an argument that this is not very different from data flow processing model, which is inherent to stream processors. So both these processing models, you can represent them as pipelines of processing units that operate over some structured data. And the processing unit in case of data flow is going to be operators such as map, reduce, distinct. And in case of data plane, these are match action tables. And the structured data that we're talking about for data flow is tuples, and for the data plane, it's packets. Now, it is straightforward to reason how we can represent packets as tuples, but how we can translate these data flow operators as match action tables is not so straightforward. So let me try to unpack that with some examples. Let's talk about a stateless operator such as filter, right? Filter will have a predicate P. It receives the stream of elements, and it will output a stream of element after applying this predicate P, right? This operator can be simply translated by supplying this predicate P to the match field of the match action table. More concretely, for the query that we were discussing earlier, here the filter, the predicate for this filter is an exact match on UDP source port, which can be implemented as shown here. So this is the case for stateless operator. We can implement map operators in a similar fashion. Let's talk about the stateful operators. Let's talk about reduce, which applies the function F. So it receives this stream of elements, and it returns a single output value, which is received after applying this function F over all these elements, right? And because this is stateful, it will require some memory. Now, this memory can be implemented in the hardware switch as hash index array, right? And to execute or to compile this operator, we will require two match action tables. So talking about the reduce operator that we have here, we will require now two match action tables. The first match action table will use the packet fields to compute the hash index, and the second match action table will apply this function F, which is the sum in this case, right? So now that we understand that we can compile or how we can translate individual operator into series of match action tables, compiling a query is relatively straightforward. We can just apply all these individual match action tables in sequence. In this case, what I'm showing you is the D1 and D2, and R1 and R2 are basically the two match action tables that are required for stateful operators, distinct and reduce, right? So now we understand that how a query can be compiled as match action tables over a switch, or we understand how it compiles over a stream processor using CPUs, right? But we need to understand that the amount of resources that are available over a switch are limited. Thus, the system actually requires a query planner, which is going to make decisions about which portion of this query should be executed over the switch and which portion of the query should be executed over the CPU. And after applying the processing over the switch, the remainder tuples will be sent to the CPU for further processing. And there are so many decisions this query planner can actually make, but for each decision, it needs to answer two basic questions. The first question being that whether the switch has sufficient resources to execute the partition query, and second question is whether the partitioning decision is reducing the workload or the number of tuples that are sent to the stream processor, right? And you will say that I'm overcomplicating this problem. This is a very straightforward question to answer if you just have one query. But in practice, the system will not have just one query. There will be so many queries here, right? And this problem will get more complicated because we have to make decisions, partitioning decisions for all these queries which will be sharing their data plane resources. So what we did was that we modeled this query partitioning problem as an integer linear program. The goal of this ILP is that we want to minimize the number of tuples that are sent to the stream processor. And this is subject to data plane constraints. And the data plane constraints being what is the size of the packet header vector, what are the number of actions that can be performed in each stage, what is the amount of persistent state for stateful operators available in each stage, and what are the total number of stages, right? And we use representative packet traces to estimate what are the resource requirements for individual match action tables, and also what is the estimate of number of tuples that will be sent to the stream processor. So now that we understand how query planner is going to make the partitioning decisions, it's going to solve this partitioning problem, let's try to understand how effective this approach is. So what I'm showing you here on y-axis is the number of tuples that are sent to the stream processor. And I'm showing you result for an experiment where we considered 8 different monitoring tasks, and the workload was 100 Gbps. So if I'm sending everything to CPU, not doing anything in the switch, the number of tuples will be order of billion for a CPU. Now, intuition is that if we can execute the stateful operators in the switch itself, then we should expect multiple orders of magnitude reduction in the tuples that are sent to the stream processor. However, in practice, we observed that the order of reduction was just 1. And this was kind of confusing for us, and we started exploring like, why are we not observing the reduction as we were expecting? And after some exploration, we observed that we were not getting the results as expected because the amount of stateful memory that was required for executing these operators such as distinct and reduce was more than what was available in the switch. So the query partitioning or query planner was forced to execute all these stateful operators in the CPU rather than the switch, and that is why we were observing that the number of tuples at the stream processor was high. So we started exploring that, is there any way in which we can reduce the memory footprint of these stateful operators? And to answer this question, we made a couple of observations that helped us. One observation was regarding the nature of monitoring tasks. For example, the query that we discussed earlier, the number of hosts that will be victim of a DNS reflection attack is going to be a very, very small fraction of the total number of hosts in the network, right? In a way, we were trying to find needles in a haystack. And we noted that this observation is actually true for most of the network monitoring tasks that we were looking at. And this inspired us to explore a technique in which we can only spend these limited resources on portion of traffic that is going to satisfy the traffic. The other observation was that we observed that with simple transformations to the existing queries, it is actually possible to reduce their memory footprint. For example, for this given query, if I apply a map operator which says like, just consider 8 bits of the destination IP field and then execute the query as is. So with this transformation, what we're doing is that we are executing this query at a coarser refinement level. But if we are just considering 8 bits of the destination IP field, then the stateful operators such as distinct and reduce will require lesser memory. So the message is that we can reduce the memory footprint of a query if we execute at coarser level. So now you must be wondering about what about the accuracy of the query, whether it will find the needles that we were interested in or whether it will miss it, right? For that, we made an additional observation, which was that if the fields that we use for this refinement, they have hierarchical structure, then we will not be missing the needles that we were interested in a way that it is possible to preserve the accuracy of the query if we are using the fields which are hierarchical. And luckily, for most of the queries that we had, the fields which were used for these stateful operators were destination IP or source IP, which have hierarchical structure. So we combined all these observations together to devise this scheme called iterative query refinement. What we do in this scheme is that we first execute the query at coarser refinement level. That is, we will transform the query, we will apply a map operator, say that we will only consider, say, for example, first 8 bits. And then at the end of this first window interval, we will get the output, which will have the query because of the choice of hierarchical packet field, will have the needles that we were interested in, but it will have some false positives also because we are operating at coarser level. Now, once we have that, what we do is like for new fresh set of packets that are coming in a new window interval, we will apply the same query, but at finer level. But this time, we will be applying a filter operator, which will make sure that it will only operate over subset of traffic that satisfied the query in the previous interval, right? So now we will apply all the similar set of operators at finer refinement level. Note that the effective memory footprint over these two intervals has reduced, but the cost is that it is taking additional time for finding the needles that we were interested in, right? So in a way, at this high level, the iterative query refinement approach is able to reduce the memory footprint for executing these queries in the switch, but the cost is that it takes additional time to find the needles that we were interested in. So now that we understand at a high level how iterative query refinement works, let's try to understand how query planner makes these refinement decisions. So for the query planner, the goal is still the same, that it wants to minimize the number of tuples that are sent to the stream processor. It is given the set of queries and the representative packet traces. In addition to the standard decision making that it was doing for query partitioning, it needs to answer a few additional questions. One is that which packet field should it use for iterative refinement? There can be multiple candidates, and it also has to make sure that they have hierarchical structure. Not all queries will have it, so not all queries will benefit from this approach also. But given the query, it will figure out which packet field is right for iterative refinement. Then what levels to use for iterative refinement, right? So in the example that I was talking about, we were saying that we will first consider 8 bits and then the 32 bits, but that approach might work for one query. For a different query, different set of refinement levels will work. So the query planner needs to figure out what set of levels to use for iterative refinement for each given query. And finally, once it has figured out what levels to use, it still needs to make decisions on partitioning, right? For each of those refined queries, it needs to decide which part of that query will be executed in the switch and which part of the query will be executed in the CPU. So what we did here was that we augmented the existing partitioning ILP and added all these questions or modeled all these questions into that ILP so that ILP can make decisions about what refinement levels to use and how to partition each of those queries. So now that we understand at a high level how Query Planner is making decisions about refinement and partitioning, let's understand what is the performance improvement here. So now, compared to the approach where we were sending everything to CPU, when we were doing partitioning, we were just getting 1 order of magnitude improvement. But with partitioning as well as refinement combined together, we are able to get 4 orders of magnitude reduction. So let me try to summarize this talk and tell you what the key takeaways from this talk are. We designed and implemented a system which is flexible. It uses, or it lets network operators express queries for a wide range of network monitoring tasks, and it lets them express those queries as data flow queries over packet tuples. And we expressed, or tried to express queries for a wide range of network monitoring tasks, which required less than 20 lines of code. The system is scalable. What it does is that it makes best use of limited resources of both programmable switches as well as the CPU. And it uses these query refinement and partitioning algorithms to reduce the workload by 4 orders of magnitude. So Sonata is a step in the right direction, but it also lays foundation for much future work. So one of the future directions that we are currently exploring is being able to monitor network-wide events. So the current implementation of Sonata is only able to identify network events at a single location, and we are currently working on how we can extend that so that we can identify network-wide events. The other thing is that Sonata, though, is capable of handling traffic dynamics by looking at the collisions and reacting to it. But we are looking at approaches in which we can make this reactive or adaptive, like make the system more adaptive by figuring out efficient ways in which, one, we can identify whether the traffic patterns have changed, and also come up with new or efficient recomputation and reconfiguration techniques so that we can update the packet processing pipeline. We have made the code for this project publicly available, and we hope that there will be some follow-up work in the future. So with that, I'll end the talk, and I'll be more than happy to take questions. Thank you.
I'm Alex Tal from Huawei. So first comment about RMT. Actually, it was invented in 2001 by Accelerated. So I don't understand when everybody showing programmable pipeline and they call it from 2013. It was 2001 accelerated architecture. Now a comment about switches, or a question. So usually switches, they're doing some things, okay? They're forwarding, they have tables, their code space, because the switches are high-end, they have a lot of optimization on area, and their tables are populated, their code space is not enough, and they have to forward packets at line rate. So have you considered a case when the switch is already doing something?
So yes, we have definitely considered that switches are not just for network monitoring. And the system is kind of modular, that it takes into consideration what is the amount of resources that are available for network monitoring. So if you have provisioned more resources for network monitoring, it will be able to do more operations in the switch. If that's not the case, then more things will be sent to the stream processor. So it's kind of like a flexible design in which you can choose that how much workload you want to send to the stream processor and provision things accordingly.
So taking from practice, usually the switches are so much populated, maybe there's like 10% of extra headroom, right? So taking a real system, does it for 10% make sense? Even trying to saying, okay, I will do something with these switches, so just will send it to the host and they will do the rest of the work.
So that's a fair question. I think it depends on what kind of target or switch you're using and what kind of resources are available. So there are different varieties of targets that are available. In our evaluation, what we did was we showed the performance of the system for different configuration of targets. So 10%. I don't know what it translates to, but we showed different configuration. And we showed like if we have lesser amount of resources available for the same settings, what is the workload on the stream processor?
Okay, thank you.
No worries.
Eitan from Mellanox. Did you consider partitioning the queries also to the NICs or smart NICs?
So yes, we definitely considered that. And so one thing is that the system is extensible. So the architecture that we have is like, we have data plane drivers. So currently we have written for the Tofino switches or other P4 behavioral model switches, software switches. But the driver can be extended so that you can kind of like use smart NICs also for that. One reason that why we kind of like didn't explore that further was that we were more interested in supporting stateful operators. So we observed, at least at the time when we were exploring this project, like stateful operators were not supported in some of the NICs that we had. So that's one reason why we didn't explore it further.
Okay, thank you.
Let's thank our speaker.
Thank you.
So our next presenter is Louis Pedrosa. He's from EPFL. He's a postdoc. He just finished his PhD at USC, and he's on the job market this year. So he's going to tell us about some really interesting work that he's doing at the intersection of programming languages and networking to tackle one of the scary problems that people have been concerned about in network functions and whether or not network functions are likely targets for attack. So as you're watching this, consider, do you want to interview him? Do you want to hire him? It's going to be a great talk. It's one of my favorite papers of the conference. So with that, I'll let you go.
Thanks, Justine. Just a moment while we figure out projection. Beautiful. I have to reboot. I don't know why as soon as I put it in. The wonders of modern projection. We can solve a lot of things in networking, but we cannot yet solve the problem of immediately projecting the moment you get up to the podium. According to this, I should be projecting.
Thank Louis again.
Thanks, Justine, for the kind introduction. I'm Louis Pedrosa. I came here from EPFL in Switzerland. And today I'll be talking to you about our recent work in automatically generating adversarial workloads. So I'm pretty much preaching to the choir with this audience, but we all know the advantages and disadvantages of software networking. On the plus side, we have all of the advantages of the software development cycle. More flexibility, decreased time to market, and decreased costs. But this also comes at the expense of the typical problems of software, the increased likelihood of bugs, and also the harder problem of inconsistent performance of running software on commodity hardware. This has real-world consequences, as an adversary can create carefully designed traffic that will slow down network functions, and this can lead to denial of service attacks and slow down the network. So clearly, we need better tools. Currently, what we commonly use today is a form of dynamic analysis known as profiling. In this analysis, we take our known test case inputs, and hopefully we do have test case inputs that lead to poor performance. Given these specific traffic patterns, we can then we can analyze the code and see exactly where the cycles are being spent, which instructions are hotter, and all of that. But this analysis can only help you if you know the specific inputs, at which point it will help you find the root cause and debug the issue. It cannot help you find the inputs that will lead to bad performance. If you want to do that, you need to use some form of static analysis. These kinds of analyses can reason more broadly about how performance works for all inputs. And within this kind of analysis, there are two subcategories. One is what we call an over-approximating analysis. This is a kind of analysis that can reason more broadly about all scenarios, even some scenarios that don't exist. So traffic patterns that may not exist, but it's particularly useful for finding bounds. It can reason about performance in a formal way, and so you have a specific bound that you cannot surpass. On a scale here that I'm showing of latency, if you have a network function that can hypothetically have a latency between 0 on the left and a hypothetical maximum for any traffic pattern at the max on the right, what we're seeing here would be a worst case execution time bound, which would be slightly to the right of that. Now, we don't know how tight those bounds are, but we do know that we can never surpass that. But the problem is, there may be no actual workload that leads to that bound, and so we don't have anything that can help us debug the problem. Now, on the other hand, we also have under-approximating analyses. These analyses are specifically designed that they can only look at that which can lead to a specific workload. And so they're always within the 0 to max region. These are the kind of analysis that we'll be looking at today, and they generate adversarial inputs, which will hopefully be as close as possible to the maximum, but still within the feasible realm. And in practice, what we see is that they're pretty close. The ones that we come up with are pretty close to what we think are the maximum. And so, now that we're more or less on the same page on what the problem I'm trying to solve here is, I suggest I propose KAUST. KAUST is our tool for automatically finding adversarial workloads. It stands for Cycle Approximating Symbolic Timing Analysis for Network Functions. As a static analysis, it takes as input the code of the network function itself and generates a PCAP file with the adversarial workload. You can then use this PCAP file with a profiler or any other existing tools to debug your performance issue and hopefully fix it. KAUST generates these workloads by exploiting two very important sources of performance variability in modern hardware, or running software on commodity hardware. The CPU cache hierarchy, which has variability between L1 hits and DRAM accesses, and algorithm complexity, where certain packets can have longer instruction paths. And in the end, it actually works. For one particular network function, we were able to increase latency by 3x. So, now that we're all on the same page, during the rest of the presentation, I'll describe how KAUST works in a bit more detail. I'll start by describing symbolic execution, the underlying technique that KAUST is built on. I'll then go into more detail about how KAUST uses symbolic execution to generate adversarial workloads. Once we all understand how that works, I will evaluate KAUST and show how the adversarial workloads that we generated measure up. I will then wrap everything up with some final thoughts. Let's get started. Symbolic execution is a special technique. It's been around for nearly 40 years now, and I'm pretty sure that most people here in the audience are quite familiar with it, but just in case, I'll go over it very quickly. Symbolic execution is a kind of code interpreter that uses a very special interpreter that modifies the way it runs the code. as it feeds values into the code, instead of assigning inputs a specific value, say 0 or 1, it assigns it a symbol. In the example I'm showing here, on line 1, when we assign an input to the variable var, instead of assigning it a number, we assign it the symbol alpha, which represents any possible value. On line number 2, when we increment that variable, it becomes alpha plus 1 for whatever value that may be, and that's the value we would return. This is easy to understand so far, but what happens when you hit a branch instruction, say an if, like what I'm highlighting right here? We don't know the value of that symbol, so we don't know which branch to take. Well, in that case, you fork execution and you take both branches. As this happens, you keep track of the constraints, the arithmetical constraints on the symbols that must hold for each of the branches to be followed, and we use a solver to check if those constraints are satisfiable and only explore the branches that are feasible. In the end, we can take these constraints and feed them again into a solver, this time to find concrete values that will make the execution path go through the branches that we were exploring. In this case here, we find that if you set the inputs to say 0, it will go through the true branch. And so now you have a concrete way of exercising that. So anyone here who's paying attention would notice this is not scalable. The number of paths that you're generating can be, in many cases, exponential based on the number of branches. Actually, in the presence of loops, that number is unbounded. This is known as path explosion. It's a very big problem in this field. What this basically tells us is that it is impractical to use symbolic execution exhaustively, at least on unmodified trivial and non-trivial code. Well, what do you do when you have a lot of work to do and you don't have enough time for it all? You prioritize. In that case, or in this case here, that's known as directed symbolic execution. You prioritize executing some paths over others based on some heuristic. Ultimately, we can reduce this down to a form of graph search and use a heuristic during the search to lean that symbolic execution towards finding paths that are more relevant. Most commonly, that means finding bugs or increasing coverage when you're generating a test suite. Ultimately, the analysis does not terminate. And so you just let it run indefinitely, and it produces results over time. Eventually, when you're satisfied with the results, or you just run out of time or patience, you press Control-C, and you have a set of results that it's produced so far. Okay, we're all on the same page on symbolic execution. Let's get back to KAUST. So the point of KAUST is that it needs to find a sequence of packets that leads to more CPU cycles per packet. That's what we're calling an adversarial workload. The analysis needs to be able to always find a sequence of packets. And so it's an under-approximation. It cannot formally produce bounds. What we're trying to find is an adversarial workload that is as bad as we can get, but not necessarily the worst one. And then the analysis is largely automated. We try to do this with as little, if any, developer input other than the code itself. So KAUST does this by attacking on 3 different fronts. On one hand, we look at the CPU cache hierarchy, and what this does is it's trying to increase the number of DRAM accesses, which leads to an increased number of cycles per instruction. We also look at algorithmic complexity, in which case we're trying to increase the number of instructions per packet. Finally, hash functions are a particular challenge, and we have some special treatment for that. So we can reverse the hash functions and expose data structure internals to then attack those using the previous 2 techniques. Let's look at these one by one. So attacking the CPU cache is something that comes up whenever we have what we call symbolic pointers. This comes up whenever you index memory with something that is based on a part of the packet. Or, as I have here in this example, you're indexing an array with, for example, the IPv4 destination address of the packet. When this happens, we need to find a sequence of packets that leads to a sequence of memory access, a memory access pattern, which will persistently access DRAM, and that definitely slows everything down. To do this, we created a CPU cache model that describes how the cache works under all of the different scenarios that we care about. The model is fairly simple. We did not need to make a very complex model for the sake of KAUST. It's just a single 1-tier model that just models the last level cache. It models contention, associativity, and write-back. Due to CPU cache slicing and the proprietary hash function behind that, we do not have an algebraic model, so we use an empirical model based on actual cache measurements that lets us understand how contention works, even despite not having full information about the processor. Now, as for algorithmic complexity, well, in this case, what we're trying to do is find a sequence of packets that leads to longer code paths. This is where we use that directed symbolic execution I mentioned earlier. Well, ultimately what we're trying to do is we're creating a heuristic to try to guide symbolic execution towards paths that increase the number of cycles per packet, all without inducing a breadth first search. Now, to estimate the number of cycles per packet, we look at a specific execution state, and we have to estimate the cycles for that one state. So we're looking at the number of cycles between receiving a packet and receiving the subsequent packet. We can add up the number of cycles up to the point where we are right now. That's easy. We already know the exact instructions up to that point. We just tally up the cycles so far while using the cache model to account for cache hits and misses. But from that point on to the point of receiving the next packet, it's a bit more difficult. There are potentially many paths, so what we have to do is estimate the cost, the number of cycles, of the longest path from that point onward. And this estimate has to be done fairly carefully. If we under-approximate, we get a weaker adversarial workload. But if we over-approximate, it will lead to a breadth first search, which will grind the analysis to a halt. Let's see how this works. So we do a very simple control flow graph analysis. And I'll walk you through an example right here on the presentation. What you have here is a very simple control flow graph for an if statement. You'll notice that the control flow diverges at one point and then converges again later on before reaching the target instruction in black, which is the point where we would receive the next packet. You'll also notice that one of the branches is slightly longer than the other one. So we start by initializing the cost of each of these instructions to minus infinity and the cost of the target to 0. And the idea is that we want to backpropagate the costs of each instruction backwards along the graph. In this example, I will be making the cost of each node 1, but in real life, we estimate the number of cycles for each instruction that these nodes represent. So as we work backwards from the target node, we end up with this point, this intermediate point here. The node I'm highlighting, though, has 2 successors. So which of the 2 successors do we take when we are adding our cost to its cost? We take the largest of the 2, so we'll take the cost of the node costing 3, add 1 to it, and continue the backpropagation. As the symbolic execution engine walks through this part of the code, it will see that the cost of going through the longer path is more advantageous, and we'll follow through with that. And so we'll explore the longer path. In the presence of loops, this is a bit more difficult. I'm going to show you a new example now with a loop. You'll notice that the edges in this graph are slightly different, so this actually represents a loop instead of an if statement. As before, we initialize the costs to minus infinity. If we just follow through with our previous algorithm somewhat naively, well, we end up with something that looks like this. So far, so good, but if you look at the node I'm highlighting, it does have a successor that costs more, so hypothetically, we would continue backpropagating. This would lead to a count to infinity problem, which would fill the entire graph with infinities, which leads to breadth first search. Clearly, we cannot do that. So we would have to use a distance vector algorithm to prevent the loop from unraveling. And that's pretty much what I'm showing you right here. But if you do that, you'll notice the estimated cost before getting into the loop is actually cheaper than the cost within the loop itself. That makes no sense. We are underestimating the loop, and we're completely cutting out the loop body. So this is a problem. So to solve that, we modify the distance vector algorithm so that we allow the instructions to show up at most twice. This unrolls the loop once, and so now the cost of the loop becomes internalized before its presence. As we use symbolic execution engine at this point, it will walk through the loop, and when it reaches the loop guard instruction, where it faces a choice of either going further into the loop or exiting, it'll notice that the cost of going into the loop is more advantageous, at which point it will greedily try to unroll the loop as much as possible. Eventually, the loop will reach its end, and the execution will continue forward. The final front that we attack on is hash functions. Hash functions pose a particular challenge in symbolic execution. If we directly try to symbolically execute them, it generates very complex expressions, and in some cases, path explosion. And yet, this is a common construct. Network functions, we need to be able to reason about the hash value that is computed by the hash function, but we cannot compute it. How do we handle that? We use a technique called havocking. This technique is based on the idea that you can annotate and disable the part of the code that we cannot handle. In this case, we remove the hash function, and we keep track of where its inputs and outputs come from and go to. Once we know where the hash value is stored, we can overwrite it with an unmodified, unconstrained symbol. Now that we have an unconstrained symbol for the hash value, we can continue symbolic execution unhindered by the complexity of the hash function itself. But now we have divorced the hash value from the packet itself, so we have a new challenge. We have to find a sequence of packets that leads to a sequence of hash values that leads to the expected behavior that we're looking at. Let's see how we can solve that. So in a traditional network function, you start from the packets and you extract from the packet a part of the packet that will be used as the input to the hash function. And then you use the hash function itself to compute the hash from that, and that will potentially lead to poor performance. Yet we have divorced the hash inputs from the hash values, so we can no longer use a solver to connect all of these things all at once. So what we do, we solve them one by one in reverse. Once we have the paths that we expect to have poor performance, we use a solver to find hash values that lead to that poor performance. Now that we have the hash values, we use rainbow tables to efficiently reverse the hash function without actually having computed it, and we find inputs to the hash function that will eventually lead to the poor performance. Now that we have the inputs to the hash function, we add constraints to the path constraint saying the symbolic expression for those inputs is equal to these values. We again use the solver, and now we can find packets that will follow through the entire pipeline to generate the bad behavior. So now that we all understand how KAUST works, let's see how the actual adversarial workloads it generates measure up. To evaluate KAUST, we used a simple testbed, 2 standard Intel Xeon servers with 10 GB NICs. We had a tester device which generated traffic using Moongen and used hardware timestamping for very precise measurement, and a device under test, DUT, where we run the actual network function. We used 11 different network functions that fall within 3 different types. We have a network address translation system, a load balancer, and the longest prefix match router. For each of these kinds of network functions, we re-implemented them with different data structures that have a different performance profile. In the interest of time, I'll only be talking about results about these 2 specific ones here. NAT with an unbalanced tree, which demonstrates an algorithmic complexity attack, and an LPM with a single lookup table, which demonstrates a cache attack. I have backup slides with all of the other ones in case anyone is interested. For each of these network functions, we used several different scenarios for comparison. As a baseline, we have a special NOP network function that just forwards packets. This is our baseline so that we can extract the cost, the baseline cost of measurement itself. We then have the adversarial workloads. First, the one generated by KAUST itself. These are about 50 flows, depending on the network function. And in some cases, we have a manual workload that was devised by an engineer based on human intuition. We then have random workloads. We start with the uniform random workload, where we have 1 million flows uniformly randomly distributed across the flow space. This is what typically is considered an adversarial workload today, and it's what you also find in many denial of service attacks. We also have a Zipfian distribution workload with about 7,000 flows. This represents modern power law internet traffic. Finally, we created a special case of uniform random, but with the same number of flows as KAUST, so that we can have an apples-to-apples comparison. Let's have a look at the first result. This is our longest prefix match network function with a single lookup table. This is a simple network function that takes a part of the IPv4 address and uses it to directly access memory. It's clearly susceptible to a cache attack. And that's what we see here. On this, I'm showing you a CDF plot. On the x-axis, we have the latency of network function, measured in nanoseconds, and on the y-axis, we have the CDF itself. The black line on the left is our baseline, the cost of doing nothing, and everything else should be measured in relation to that. All these lines here in the middle represent our typical internet traffic, including our Zipfian workload. And on the right, you'll see the adversarial workloads, both the Castan one and the uniform random one. But when you take uniform random and put the same number of flows that Castan has, it barely shows up on the map. It's the same as your standard traffic. The key takeaway is, well, Castan was actually able to induce a persistent DRAM access pattern, which was able to increase latency by a factor of 3. This was about the same as uniform random, which is what we would expect to be the worst case scenario for this network function, but uniform random uses 1 million flows and Castan uses 50. Even when we force uniform random to use the same number of flows as Castan, it barely makes a difference. This also has an effect on throughput. As you can see here, Castan drops throughput compared to traditional internet traffic by 19%. So now let's have a look at the NAT box using an unbalanced tree. Now I think we can all agree that an unbalanced tree is an unoptimized data structure that no one should be using in production. But sometimes bad code makes its way to production, wouldn't be the first time, and it's nice to have a tool that helps you understand what happens, and so you can solve and you can debug and fix it. Again, this is a CDF. The x-axis is the latency and the y-axis is the distribution. The black line on the left is or not. What we see here is that the performance doesn't depend just on whether the traffic is adversarial or not, but also on the sheer volume of traffic. And the uniform random is way to the right just because it has 1 million flows. But the Zipfian traffic workload is still slightly to the left, even though it has 7,000 flows. The Castan workload, which has about 50 flows, is doing about the same as a manual one, which we carefully crafted to skew the tree. And this is despite having 2 orders of magnitude fewer flows than the Zipfian workload. The takeaway here is, yes, Castan, even in these specific scenarios, was able to find a pattern that skewed the tree very specifically, and that this increases median latency by 70%. The throughput in this case was modified to a lesser degree, only by 7%, but it was able to come up with a pattern that was pretty close to the manual workload. And the manual workload requires an engineer to devote some time and pay their attention and learn how the network function works, to use their intuition. Castan does this automatically without developer input. With that, I conclude my talk. Today I talked to you about Castan, our system that automatically generates adversarial workloads. It does this by attacking algorithmic complexity, the CPU cache hierarchy, and by carefully reversing hash functions to expose data structure internals. It does this with little, if any, developer input. The adversarial workloads that we come up with are about the same as manual, but without requiring human intuition, and they do far better than uniform random when compared with the same number of flows. In one case, we increased latency by 201% and dropped throughput by 19%. If you're interested in finding out more, I encourage you to seek us out. We have a poster downstairs in case anyone is interested, and all of the resources regarding this, the paper, the poster, and the source code are all available online on the link that I'm posting up here. Thank you very much. I'm happy to take your questions.
Hi, Marco Canini from KAUST. Thanks for the wonderful presentation. So the work is very interesting, and you convey quite nicely, the high level inner working for symbolic execution. But I'm trying to develop a little bit more intuition as to why Castan would want to produce more than one single flow. So if you think about network functions, much of the code, if it is doing flow-based analysis, it would ask the question, is this packet belonging to an existing flow, or is it packet belonging to a new flow, right? So there is this branching point in the code, and subsequent to that, much of it will be uniform. So you were showing this adversarial workload with, you said 50 flows, but I don't quite understand, how you would come up with those 50 flows, given that what you're trying to produce is a path that has a higher cost.
Right. So my apologies, I meant 50 packets. Castan itself does not have the notion of a flow. It's something that emerges, and we just measure number of flows from the PCAP file that it produces. As we run Castan, we tell it how many packets we want it to run. Essentially, when I mentioned that we run the analysis indefinitely and press Control-C, there is a parameter to Castan that says, you can stop at X packets, and that's what the PCAP file will have.
All right, thanks.
Hi, your time recall for UC Berkeley. I wanted to ask, in the evaluation, you said that the main impact is more DRAM access. So I wanted to ask whether this is due to additional instructions or more like additional cache misses.
So DRAM accesses is the most expensive of these, yes. And that does not infect the number of instructions. It's a single instruction, typically a read instruction or a load instruction, which will have significantly more cycles due to the DRAM access than if it were an L1 hit or any other kind of hit.
So most of the effect of Castan is cache misses, causing cache misses, like the adversarial workload that you create. Does it cause more cache misses, or does it cause more like longer executions?
Castan tries to do both, and depending on the structure of network function, one or the other.
No, but what did you find like in reality in your experiments? That's interesting.
It works for all of those, and different network functions have different cases. The DRAM accesses have the highest costs because it's the one case where you can have something like 3x.
Yeah. Okay, thank you.
Thank you. Yes.
Take one more question while we're setting up here.
Hi, Sanjay from Purdue. I enjoyed your talk. So a question for me was, is there anything specific to the networking domain that you're exploiting to make this work? And if so, what? Or is this more generally applicable, the techniques that you have developed?
Thank you. That's a very interesting question. The technique overall is not specific to networking, but it takes advantage of several factors that are common in networking. The technique does not scale to extremely large programs, so you wouldn't run this on, say, a MapReduce. But because it's exploiting these low-level features that have such an important factor on network functions, because they run typically with a very small time budget, 150 nanoseconds or so, that's where it's most advantageous. We also take advantage of the fact that networking has a very specific structure to its inputs. We know exactly inputs come from packets, and they only come in through the receive function, and it's very well-structured code, and so it makes the analysis much easier to automate.
Okay, thank you.
Thank you very much.
Let's thank Louise. Our next speaker is Kai Gao. He just graduated from Tsinghua University. He also has a new job. Where are you headed?
Sichuan University.
Congratulations.
Thank you very much.
He's going to talk to us about Trident, which is a unified SDN programming framework.
Thank you very much. Thank you, Justine. Good morning, everyone. My name is Kai, and it's my great honor to be here and present Trident toward a unified SDN programming framework with automatic updates. This is also a joint work with my collaborators Taishi, Nojima, and Rishabh. Taking the control plane out of distributed boxes, SDN simplifies network management with logically centralized network control. At the same time, a lot of network functions are also deployed in the network. After analyzing the traffic, they can extract useful information such as whether this host is a heavy hitter or what is the geolocation of the host. These informations are layer 7 informations, and combining these two technologies into a unified programming framework, we might be able to enable adaptive and cross-layer network control. So a network program can react dynamically to the characteristics of the traffic and also control the traffic based on layer 2 to layer 7 information, as we refer to it as unified SDN programming. So in the talk today, I want to talk about what are the design challenges of a unified SDN programming framework and why are existing SDN programming frameworks not sufficient to do the job. So the first challenge is how to integrate network function state into SDN programming, because the state-of-the-art SDN programming languages support layer 2 to layer 4 programming very naturally because all these information are contained in every single packet. However, for network function states, as we discussed earlier, they are like layer 7 information which are not contained in packet header fields. And for example, the HTTP host information, before you establish the HTTP, before you exchange the hello, before you finish the handshake of HTTP protocol, you do not have the information about whether the packet belongs to a certain HTTP request. So there can be unknown information, and because they are modeled as state machines, they could constantly be updated by the state machines. So we need a simple abstraction to encode these layer 7 information into SDN programming. And the second challenge is to construct consistent and curated routes. The problem is that a lot of network functions require certain symmetry requirement about the traffic, because, for example, the deep packet inspection, they probably require the packets for each TCP connection to go through the same instance. And without the ability to describe such correlations, people might define the routing for the packets in both flows independently, and that can cause a problem because, for example, in the example we demonstrate on the right-hand side, the forward path, basically the red one, goes from the host to DPI node 1 and then to the internet. But if the return shortest path is calculated also using the shortest path algorithm, then it might choose the blue path. And the consequence is that they do not go through the same DPI node, and the DPI node cannot work correctly. So we need to systematically construct these consistent and correlated routes. And to address the aforementioned challenges, Trident comes up with two programming abstractions, basically the stream attribute and also the route algebra. The stream attribute is to encode network function state as if they are like header fields, so that programmers can select packets based on these attributes. And the route algebra is a simple yet flexible abstraction to systematically construct consistent and curated routes. After that, people might think that, okay, we have very simple abstractions to do the match and action for this unified SDN programming framework. However, there's still another problem that we have to handle dynamicities caused by network functions. Because a lot of network function states are dynamic. So when a state of finished state machine change, the corresponding route may also have to change. And if we want to identify all these dependencies to handle these dynamicity manually, it can be very complex and error-prone. So in order to solve that problem, I try to introduce the abstraction of live variables and to handle the dynamicities of both stream attribute and also the route algebra. Now, after we're giving some high-level instructions to the pieces, now we want to show us how we can actually work with these abstractions. So now I give the workflow of Trident. First, a network operator or the programmer has to specify the data schemas for network function states because if you don't know what it is, you cannot use it. And then the network functions must implement this schema so that they can correctly transport the information to the Trident system. And then a programmer can submit the network control program to Trident, and Trident will evaluate this program and calculate the corresponding routes for with the information in hand. For example, maybe with some unknown network function states at first. And after installing the flow rules, the packets start to go through the network functions, and the network functions can update the state. And also, the changes could come from like configurations and also configuration changes and also the topology changes. And all these changes are handled by Trident in a unified way. And then Trident checks whether the data plane configuration is consistent with the control plane state and automatically updates the routes if necessary. So after giving the workflow, now we go into the details of each abstraction. The first abstraction is called stream attribute. Stream attribute is based on the observation that different network function states are computed from different sets of packets. For example, if we consider an attribute called HTTP URI, because HTTP connections are basically carried out by TCP connections, so this information is computed from packets of the same TCP connection defined by TCP5 tuples. And for header detection, here we only consider the source address, then they are computed from packets with the same source IP address. Now we give examples of how we can define a stream attribute. So we need the following information. First, you need to specify, okay, what type is for this stream attribute. For example, the HTTP UI here, then it's always encoded as a string. And maybe for some, like traffic volumes, they probably encode it as integers. And then we need a second parameter, basically a descriptive name to describe so people can understand what this attribute means. And eventually we have to also give the stream type. Basically it's bit masks on packet header fields, specifying how the set of packets are composed to compute the network state. For example, it can be like TCP5 tuple for HTTP UI information, source IP address maybe for headers, and maybe this IP address for some other attributes. And after we define the stream attribute, we can just use them directly, just like a packet header field. And as we mentioned earlier, stream attribute can have an unknown value. And instead of, for example, in other programming languages, you probably handle them as null values or some other abstractions, and Trident treats unknown values as basic data type and use clean three-value logic to select packets based on stream attributes. And below is an example of the truth table of the clean three-value logic. And we also, to simplify the handling of these three values, we also introduce some customized control structures, both as language candies and to avoid ambiguity of the two-way branch. And now we introduce abstraction of algebra. So the objective of algebra is to use well-structured declarative expressions to specify the construction of consistent and correlated routes. So this is motivated by prior studies such as waypoint-based routing and relational algebra. And different from these approaches, we consider the basic unit of algebra is a route set. So you can consider it's like we are doing some similar stuff to relational algebra. We're selecting the routes with certain conditions from a given route set. And I think that basically gives us a simpler understanding of how things are going. And then each route set has a network function indicator to indicate whether the traffic should satisfy some symmetry requirement of the given network functions. And we also have defined some operators to help people compose more complex route constructions. And now we give an example of how people might construct a desired route using route algebra. For example, if a programmer wants to define the route for a flow from a host to a gateway with link capacity preferences. For example, they prefer higher link capacities over the lower ones, for example. And for the first step is I want to compute a primary route set with a high link capacity. Basically, this can be expressed using a selection operator on top of the enumeration of all the routes in this network. And then we can compute the backup route set with like 10 gigabyte links. And now we have two route sets. We can use the preference operators to combine them together. And after that, because we are only considering the routing for a single flow, so we only need one of the routes from the route set. So we use any operator to select a single route. And now we give some details about the live variable. So live variable, the objective of live variable is to make dependency tracking and updates transparent to programmers, so that programmers only need to remember the abstraction of stream attribute and route algebra and need not worry about the dynamicity caused by the network programs. Live variable is motivated by functional reactive programming, so it is a traceable data type which not only stores the data, but also the computation process. And stream attribute and route algebra are just higher abstractions of live variables. And the updated live variables satisfy the glitch-free consistency, which is an important property in functional programming systems. And now we use an example to demonstrate how everything ties up together. With the example program blocks traffic for infected hosts and construct route using a concatenation operator. So there could be multiple events. First, for example, we consider a typical case of topology change, and one of the routes becomes invalid, and using the route set, we might just pick another one from the same route set, and we can just, the Trident system would automatically recompute the concatenation of these two new routes. And if the host status changes to infected according to the program, the packet should be dropped. And when the host status is cleared, for example, through an enemy interface or triggered by a timeout event, then basically it means we are back to a normal status, so we will start to forward in the past, and then the new route will be automatically recomputed. After giving the details of the abstractions, now we start to dive into some implementation details. And one of the highlights in our paper is the efficient update. Basically, it gives as the performance gains. And the objective is to leverage semantics of operators to achieve the fast updates. Because if we only use general like glitch-free consistency updates, then we still have to wait until all the computations are finished. But since we are developing more like a domain-specific language for network programming, so we can leverage the semantics of certain operators. For example, we consider the preference operator. Basically, the preference operator works in the following way. If I have a route A and route B, and I prefer route A, so whenever A is available, I will not use route B. And we can implement this policy in this program. We first construct a primary path using the shortest path algorithm, and then we can construct a backup path using like unique protections. And whenever a data change to a topology, which triggers the invalidation of both paths, so they are not available, we have to recompute them. And whenever the primary path is available, we don't have to wait for the backup path to be ready, and we can already use the primary path. And we use we give a more detailed description of how everything works. And at the time 0, because we don't have any route at the moment, and the shortest path still in the calculation process, so we don't have any route. And then after the shortest path algorithm is finished, the primary route P0 is ready. And with efficient update, we can already select P0 as the desired route. But if we use like glitch-free consistency as in traditional, in a general functional reactive systems, then the system has to wait until the calculation of the backup route is finished. And that's what happens when at time 2, the backup route P0 is also ready. Then the standard update will select the P0 as R. And we can see that even though after the time we eventually select the same result, but with efficient update, we can save some time. At time 3, we consider a data change. For example, a topology change that invalidates primary route, but the backup route is still available. And at that time, because according to the semantics of preference operator, we just select the backup path B0 as the desired route. And at time 4, when the second shortest path algorithm is finished and the P has a new value P1, and with efficient update, again, we can select P1 as R without waiting for the backup path to be ready. So with this simple code, we demonstrate that Trident achieves a lifecycle management for backup routes. And this is not just, for example, a special case. Actually, we can also, in the paper, we also prove that for all route algebra operators, if the partial result has no unknown subsets, the output guarantees glitch-free consistency, and we can apply efficient update. And now we go to some evaluation results. Due to the time constraint, we only consider 2 evaluations in a talk. So here is our evaluation settings. We build our prototype on top of a commodity server, and we measure how difficult it is to integrate network functions into Trident by quantifying the efforts using the additional code. We consider 2 use cases. The first is the BRO, a data packet inspection framework, and the second is for Radius, an open source Radius server. And so we summarize the results in the table, and we can see that with tens of lines of code, we can already integrate these 2 network functions into Trident. And we also demonstrate the benefit of efficient update using some micro benchmarks with the program we demonstrated earlier. And we measure the recovery time for a single source and destination pair in 4 different topologies. We compare the results of the initial computation and also the fast rerouting stage, and also compare the time taken by the standard update method and the efficient update. And the results are given, so the results for these topologies are listed in this page, and we can see that the first bar of each graph represents the ready time to get a path using the standard update method, and the second bar is the time taken by efficient update at the initial stage. And we can see that we can actually reduce the time because we don't have to wait for the backup hash calculation to finish. And for the fast rerouting stage, both approaches can reduce the time significantly, but because we have the backup, because we use raw algebra to define the backup routes ahead of time, so they can be installed without waiting for the new shortest path to be ready. And we have demonstrated that an improvement up to 39% in initial computation and improvement of 1 to 2 magnitudes in the fast rerouting stage. Okay, to summarize the paper, Trident is a unified SDN framework with some novel abstractions, such as stream attribute, raw algebra, and live variables. And we are able to achieve a more general intent network framework. Right now, we are still limited to the write-only network functions in the sense that these network functions only update the state without to the trans system without reading it from, for example, the configurations from the trans system. And we plan to expand the scope and basically to more generic network functions. And also, we think with the abstraction of live variables, it could also help people to verify the network policies behaviors. Okay, thank you for attention. I'm happy to take any questions.
Okay, Wenji from Fermilab. I have a question. A lot of traffic is encrypted, so how you handle the high-level tuples?
That's a good question. So right now, we still rely on the capabilities of the network functions to handle, for example, the encrypted traffic. So if the network function is unable to, for example, decrypt the traffic, then there's no way we can solve that problem.
So I had another question for you. You talk a lot about your new abstractions here. What are the limitations, or is there anything that you found hard to encapsulate in this model?
Yeah, at the moment, because we still basically in the beginning we just build everything from scratch, like using the raw sets, and then it might occur to people that what if the raw set returns an empty set, and it may not be efficient to enumerate all the routes and then start to select routes from the raw set. And I think one challenge is to whether we can do it in a more like top-down way. If we know what the program specifies, okay, I want some kind of routes, and is it possible to generate the routes in a top-down way? I think that basically, this is related to the efficiency of how you can scale well with a lot of requirements, because if you, especially if you are in a very large topology, so you can see that in our evaluation, we still consider relatively small topology so that we can use the naive way, and I think that's a problem. Yeah, thank you very much.
So our next speaker is Nofel. He is just finishing his first year at Penn, and he already has a SIGCOMM paper. And he is looking for internships this next coming year. He's going to tell us about synchronized snapshots with a system called Speedlight.
Okay. Thank you, Justine. My name is Nofel, and today I'm going to talk about why we need network-wide measurements and how we can get them. Measurements is how we answer questions about the network. Operators need for configuration, management, and provisioning. Architects need for new protocols and topologies. Researchers need for measurement, studies, and evaluation. Today, how we conduct measurements is generally one of two ways. The first and most common approach in understanding network behavior is to measure individual network components directly. This can be in the form of counters, packet sampling, or even hardware-supported metrics. The other method is to move beyond single component measure and use end-to-end or path-level tools. Examples of this include ping, N-band network telemetry, or ACN. Both of these techniques have enabled us to solve many challenges over the years. However, there is a large class of questions they still can't answer. I'll give you a simple example. Imagine we have a small topology with 4 switches A, B, X, Y. As you can see, it is an asymmetric topology as there is a missing link. Now imagine we observe a packet traveling from B to Y and then getting dropped. What is the reason for this packet drop? Well, there are few possibilities. One possibility is that the drop is due to congestion. In this case, both the queues at the queue at X and the queue at Y are full, and therefore the drop was unavoidable. We could have only prevented a drop if we add capacity to the network. Another possibility is our load balancing protocol made the wrong decision. In this case, the queue at X has additional capacity, but A is sending data to Y anyway. This may indicate a problem with the load balancing protocol. These two cases are both possible explanations. If we were able to measure both queues simultaneously, we would have been able to distinguish between them. Unfortunately, modern tools don't have this ability. Tools that measure individual devices may be able to show you the Y has full queue or X has a full queue or an empty queue, but cannot say whether those states occur at the same time. Particularly in the case of bursty traffic, and recent papers have shown that in modern large and fast networks, bursts occur in microsecond scale. We can also measure entire paths, for example, by tracing the state from A to Y or A to X, but the problem is they cannot tell us the state simultaneously. The key observation we make in this paper is, if you can take one thing from this talk, it should be that existing tools fail to capture simultaneous behavior. So how do we get this type of global view of the network? Ideally, we would like to capture the entire state of the network at a single point of time. Unfortunately, such strict consistency is impossible without atomic clocks or freezing the network. Instead, we aim to have a set of data plane measurements that capture the state of the network at an approximately single point of time. We do this by providing two key properties. The first is causal consistency. Causal consistency means if a measurement includes the effect of a particular event, then all events that led to that particular event should also be included. Causal consistency is necessary, so our set of measurements actually makes sense. The second is near synchrony. Near synchrony means to have an upper bound when it's the time difference between when we record the last component in the network and the first component in the network. Ideally, we would like to be less than RTT, so our captured state is actually close to the actual state. Together, these two properties preserve the most useful metrics. Okay. To meet this goal, we implemented and deployed SpeedLight in P4 switches. SpeedLight captures network-wide state, or in other words, takes the snapshot of the network. This state could be any data network admins wants to record and is supported by the P4 program. SpeedLight is designed to operate even if the subset of the switches are running SpeedLight. Our results show that the synchronization is less than 100 microseconds, which is even for large networks, which is within the RTT of most LANs. Before I move on, let me give you outline of the talk. First, I'm going to talk about a classic algorithm that forms the base of our system, the Chandy-Lampert snapshot algorithm. Then the challenges of taking snapshots in the network. Then I will describe protocol and the prototype implementation. Finally, there is evaluation, in which I will show that we were able to complete the snapshot more than a magnitude faster than the current mechanisms, and some interesting insights about data center workloads. So first let's talk about what it means to have a global view of the network. One way is to get local state of every node. In distributed system, we call the collection of local states a cut. A cut partitions the network into pre and post snapshot. Let's say we make a cut and we get something like this. This cut is inconsistent because we see that the server B local state shows a packet received, but according to this cut, no machine in the system has sent the packet. Instead, what we want is a consistent cut, something like this. A consistent cut is defined as the state of the network captured such that no effect is seen without its cause. Chandy-Lamport is a classic algorithm that determines the state of a distributed system during computation by making consistent cuts. It is completely asynchronous and it ensures causal consistency. Now let me walk you through how Chandy-Lamport algorithm works. Let's say we have 3 servers A, B, C, and we want to take its snapshot. Our messages carry the snapshot number. When we initiate the snapshot, the observer process, the process that's taking the snapshot, saves its own local state marked by a star, sends a snapshot message to all other processes, and starts recording. When the process receiving the new snapshot ID for the first time, it saves in own local state and then attaches the new snapshot ID to all the subsequent messages and also starts recording at other channels. Snapshots are completed when servers have received snapshot token from all other neighbors marked by a circle. If during the recording phase there are any packets between the star and the circle, they're considered part of the channel state. Chandy-Lamport is a nice starting place because it was designed for distributed system. However, enhancing it to a switch level poses multiple challenges. First, and one of the biggest criticism of Chandy-Lamport is it does not have an upper bound when the network-wide snapshot will be captured. As it is asynchronous, it can take a long time, and we want something close to an actual state. Second, Chandy-Lamport also assumes that the nodes are single-threaded and have FIFO channels, whereas modern networks are highly parallel. Each port in the switch essentially can process at the same time. Third, Chandy-Lamport assumes general-purpose CPU, and programmable data planes have very limited computing power. Sending packets to the control plane is no better than sending packet to a remote host, as they both incur overhead and it breaks both of our desired properties, causal consistency and near synchrony. Now I will tell you solutions for these challenges, and along the way, we are going to learn how Speedlight works. First, let me introduce to the various components in our system. Consider small cloud. We have an observer system under network admin and a small topology with 5 switches. Each switch has its own control plane and data plane. Our first challenge was that Chandy-Lamport have no upper bound when the snapshot will be completed. To resolve this, we do 2 things. First, we synchronize time and we enlist every switch to start the snapshot together. Before taking the snapshots, we synchronize routers using Precision Time Protocol, or PTP for short. It is not perfect, but does a good job to synchronize clock in microseconds. Snapshots can be initiated at any switch in the system. So we start the snapshot at multiple switches in the system, and an algorithm will still be correct. The proof is given in the paper. Initiation is as simple as sending a packet to some port in the network with an incremented snapshot ID. A snapshot ID is piggybacked on regular traffic, but the control plane has the option to send null messages with an updated snapshot ID. So we schedule a snapshot number n at time t at all the switches in the system. At time t, the control plane then sends the packet to the ASIC with the incremented snapshot ID. As all the switches start the snapshot at approximately at the same time, it gives us a very tight upper bound. Our second challenge was that Chandy-Lamport assumes single-threaded channels and FIFO single-threaded CPU and FIFO channels. However, modern switches are highly parallel. They can process multiple packets at the same time. A naive implementation will fail us to provide causal consistency. To resolve this, we break down the network into its most fundamental components. Here you see we divide the data plane into ports into 2 components. We separate out the ingress and the egress. The red and the blue lines in the diagram shows queues for different class of services. Despite aggressive amounts of parallelism, for a single port, single direction, processing is guaranteed to be linearizable. This breaks down the challenge of parallel processing and priority. As I mentioned in the last slide, CPU sends the incremented snapshot ID to the data plane. When these packets arrive at the data plane, each port records its own state and then piggybacks the new snapshot ID to all the packets it forwards, regardless of the destination. An issue might be, what if the new snapshot ID from the CPU does not reach the data plane or it is delayed? In this case, each port will take the snapshot when it receives the packet with the new snapshot ID from the neighboring switch. Essentially, if the packet contains the new snapshot ID, it does not matter whether it receives from the neighboring switch or the control plane. The use of snapshot information in the packet header also makes it resilient to packet drops. Our third challenge was Chandy-Lambert assumes general purpose CPU. Programmable data planes have limited computing power. They have limited programming model, space, and number of RAM access at line rate. This makes it difficult to complete the snapshots and handle many edge cases, for example, lack of traffic where ports don't see update from the neighbors. Control plane is responsible for compensating for these deficiencies. For completing snapshots using control planes, we need to answer two questions. How does the control plane know when the snapshot is completed, and how to collect the snapshot data? In Chandy-Lambert, we know the snapshot is completed when a server receives the latest snapshot ID from all the neighbors. The case is similar in SpeedLight. A port has completed the snapshot when it has received the latest snapshot ID from its upstream neighbor. To propagate this snapshot to the control plane, data plane sends notifications to the control plane and can detect completion of snapshots. Looking at the notifications, control plane can detect completion of snapshots. Once the snapshot is completed, control plane can simply read the data directly from the RAM. Lack of traffic can make snapshot inconsistent, as some port will not be able to complete. In this case, we force the snapshot through broadcast. There's also a possibility of some port of link going down or notifications being dropped where we are unable to complete the snapshot. Let's say some port goes down and then we see a snapshot ID jumping from 5 to 10. In this case, we conservatively mark the snapshot IDs as 6 to 9 as inconsistent. Handling such cases, we end up with a bipartite design. Data plane is responsible for core of the protocol, the processing required in band, whereas the control plane is responsible to fill in the gaps. Now let's come to the implementation. We implemented a prototype of SpeedLight, including all of the control plane and data plane in barefoot to Fino switches. For evaluation, there are several questions to be answered here. How well does it synchronize? What is the overhead? And what it can show about us, the network. As shown in the picture, we had only one hardware P4 switch, and to faithfully emulate a large network, we sliced the hardware switch into 4 independent virtual switches. Having a shared CPU among the virtual control planes creates a bias in synchronization time, because having the same processor means virtual control planes were also sharing the same clock. And our goal is to minimize the synchronization time. Therefore, such bias was unacceptable in the same clock in the experiment. To handle this bias, we move the virtual control planes to external machine. This technique provides isolation among virtual control planes and make them completely independent. This gives us a small leaf-spine topology with 4 switches and 6 servers. We began by evaluating synchronization properties of SpeedLight. This experiment captures how long does it take for SpeedLight to capture the state of the network. We schedule a snapshot at virtual control planes at time t, specified in microseconds. The virtual control planes send initiation packets to all the ports in the switch. We then compute the synchronization time by taking the time difference between the earliest and the latest timestamp across all ports. For comparison, we also measure the time difference for a typical counter-polling framework similar to modern systems. When observer polls statistics from each port individually, we a control plane agent that reads and returns the value on demand. On median, it takes us only 6.4 microseconds to capture the state of the network, whereas for polling, it takes a few magnitudes higher at around 3,500 microseconds. Next, we evaluate how SpeedLight scales. For this experiment, we ran a similar experiment with the previous one, but over a large simulated topology and using 64 port routers. The figure shows average whole network synchronization time. Our simulation includes PTB time drift, open networks Linux scheduling effects, and the latency between initiation and completion of snapshot. We note that speedlight initiate at every switch. Additional routers have limited effect. How- However, additional ports and router can make encountering tail effects more likely. This effect still remains typically under RTTs. There are few overheads involved in the network when we implement speedlight. As P4 switches compute at line rate, we do not add any latency. Our additional header in the packet takes 8 bytes per packet. However, we use 16 bits per integer. If an operator can work with fewer bits, it will take much smaller. We use 24 stateless and 11 stateful ALUs. This is out of 384 and 48 respectively. However, traditional switches are constrained by memory, not by CPU. We have a low memory overhead. To save one snapshot of all ports in the switch, it takes few kilobytes depending on the metric that we are measuring. These resources are for 100 snapshots saved in the data plane at one time, and also include the forwarding rules of our small topology. These numbers are just for reference. We can take more or less memory or CPU depending on the number of snapshots and the metric that we are measuring. For instance, we compiled a version that uses 17 stateless and 9 stateful ALUs. It depends on the metric and what network admins wants to capture. So let's come to the use cases. The first use case we target is detection of synchronized application traffic pattern. For this experiment, we measured weighted moving average of packet weights at all egress ports. We take 100 snapshots at 1 second interval and then calculated the pairwise correlation between the ports using experiment tests. To read the graphs, I'll give you a simple example. Let's say we are reading correlation between port 1 and port 9. These boxes are color-coded. In speedlight snapshot, we see a high correlation as the value is close to 1, and in the polling mechanism, we have no correlation as the value close to 0. So overall, the experiment test found for speedlight, we have 43% higher correlation. To validate the correctness, we analyze the output evidence of 2 ground truths related to the application traffic and network topology. First, we expected to see no significant correlation between port 0 because it is a master server and did not participate in the computation. The second is we expected to find high correlation between possible ECMP next hops. With a snapshot, the correlation coefficients match both expected ground truths. Polling, on the other hand, failed to identify the positive correlation between ECMP ports. As shown by the red boxes, the correlation found with polling were either statistically insignificant or worse, statistically significant but negative. The goal behind this experiment is to show that snapshots can reveal ground truths to us and help debug applications or optimize network protocols. Now let's move to the second use case. So we evaluate is my load balancing protocol working? We demonstrate Speedlight's ability to answer this question by comparing performance characteristics of ECMP and flowlets. In theory, flowlets should balance more fairly because it splits on traffic bursts rather than packet floats like ECMP. To measure this, we computed standard deviation of weighted moving average of packet enter arrival times across the uplink ports. Based on the measurement from Speedlight, we see a few effects. In the Hadoop workload, we see that polling is unable to differentiate between ECMP and flowlets, whereas in reality, there is a difference. Next, for Memcache, note that for Memcache, the units are in microseconds. We see that Memcache is consistently very balanced because the flows are extremely short and our workloads were relatively balanced. We see that polling consistently overestimates the balance. Averaging over long periods shows a perfect balance in both cases, and together these two experiments show that polling might not just provide an incorrect view of the network, but also difficult to put a bound on the inaccuracy. Let me summarize everything. We demonstrate that it is possible to take high-resolution network-wide snapshot with programmable data planes, which gives us causal consistency, and the entire network state can be recorded in less than 100 microseconds. We have implemented it on P4 switches, and we have released our code on this link. Thank you. Any questions?
Any questions? So I was wondering if you could share some more use cases. I mean, this is clearly a really novel primitive. I've never seen something like it. It's super cool, but what else could we use it for besides the examples you gave us?
So one thing that I was thinking, like Sonata was implemented, they have a query-driven language. So they actually talked about having network-wide events. I think this can be used there also. This is one example.
Cool.
Hi, Miguel Neves from UFRGS in Brazil. Which type of metrics are you able to collect from your network, and how do programmers specify them?
So we can program in a P. So if our metric is supported by the P4 program, we just have to point it in the direction of our code, and it can capture it. So we tried it for QDAP, utilization, packet counters. These are something that we have tried.
Okay, thank you.
Way back from the Microsoft Nest Talk. So together with network snapshot, I actually have a very simple solution. So I can use PTP to synchronize the time of the switch CPU. And then when I put a counter, I also record the timestamp. So what is the advantage of your scheme compared to my simple heuristic?
Okay, so it will not give us causal consistency, and we have causal consistency, and it does not record channel states, and we have channel states.
Okay, I see. Thank you.
Let's thank Nofel and all of our speakers, and then we'll see all of you back at 11.